Yeah, so in this set, this particular set is referring to this portion, the white portion over here, and xn minus m alpha is referring to the white portion over here. So therefore, it is clear that since beta is sending everything, the whole xn to the image, and then we are removing this part of m of beta, so therefore this portion over here cannot be greater than this set over here. So therefore, we will always have, because this is image, we are talking about the entire set xn, and so it's not possible, since this xn is a mapping from xn to xn. It is not possible for the image set to be greater than the domain, or the domain of the mapping. So if you think of this part, this set here, as the image of this white portion over here, and then so that means you have a mapping beta from here. You think of the restriction of beta from this part to this white part, then it's not possible for since the restriction of beta on this, it is not possible for the image or the codomain to contain more element than the domain, because if that happened, then the image set cannot have more element than the domain, because if that happened, then you are saying 2 points must have two different images. A single point, a single point is having two different images, but that is something that cannot happen for a mapping. And so therefore, this part, this white part, is always greater in size or equal to this white part over here. And that is the observation we are trying to make here. So we are saying that the cardinality of this set, the white portion of the image of beta, must to be less than or equal to the cardinality of this set, which is the white portion inside the domain of beta. The white portion, that is the complement of the image of alpha. And so once this is settled, then we have that the defect of the product being the cardinality of this set, that is the cardinality of this set, must be equal to the cardinality of this part plus the cardinality of this part. This is because this product, this union here, is a disjoint union, so you can just add the two cardinalities. But then this part is less than or equal to xn minus m alpha, the size of that, so we have less than or equal to this. So this is exactly what we call the defect of alpha, and this is the defect of beta. And so therefore, we have defect of the product to be less or equal to defect of the sum. So this is establishing the lemma. Now, as a corollary to this lemma, because you have defect of the product and is less or equal to defect of the sum, and you remember by our very definition of the defect, we said it is n minus the height. So if you substitute defect to be n minus the height, defect to be n minus height, you will have this inequality. And this inequality is giving us a lower bound for the height of alpha. So we saw that the height of alpha is always bounded above by the minimum of the height of beta or the height of alpha. But then that is height of the product is always bounded above by the minimum of the height of its factors, and also it is bounded below by this sum over here. So therefore, it cannot just keep going down indefinitely. It can go as far down as this integer over here. There are more integer functions associated with a finite full transformation. For example, we have the concept of fix of alpha, and all of this will play a role in combinatorial and algebraic study of the finite full transformations, more especially when one is looking at product of idempotent and other also combinatorial aspect of the finite full transformations. So the fix of alpha is the set of all elements in Xn that are fixed by the map. Likewise, the shift of alpha will be the set of elements, that is the cardinality. Actually, fix is the cardinal number of the set of all elements that is fixed by the map. Likewise, the cardinality of the set of elements that are shifted by the mapping is denoted by S alpha, and it is called the shift of alpha. And then because out of n, if you subtract the fixed, then you will have the shift. The number of cyclic orbit of alpha is called the cycle of alpha, and it is denoted by C. Remember, every full transformation or finite full transformation can be decomposed into orbits. And we say orbit are of 4 kinds. We have the cycles, the trivial orbit, the acyclic orbit, and the standard orbit. So the number of cyclic orbits is called the cycle of alpha, and we denote it by this. This parameter or this particular integer will play a role in our study of product of idempotent. Likewise, the number of acyclic orbit is written as A alpha, and the number of trivial orbit will be written as T alpha. And from the very definition of this A alpha and trivial orbit, because every acyclic orbit contains a fixed point and every trivial orbit is also a fixed point. So we immediately see that the number of fixed points of alpha can be achieved by counting how many acyclic orbits plus how many trivial orbits are there in alpha. So thank you very much for being with us, and I hope to see you in the next lecture.